Newton's third law of motion. I can investigate and describe applications of Newton's third law.
Welcome to the International Space Station. I'm NASA astronaut Mark Vanderhei. Today, we're going to talk about Newton's third law. How do you think it will hold up in microgravity?
For every action, there is an equal and opposite reaction. This means that in every interaction between two objects, there are a pair of opposite forces acting on each object at the same time, a force pair. You can see that there are many examples on Earth. In space, thrusters expel one way and the vehicle is steered in the opposite way.
Although again, more basketball stunts that I can't do on the ground, at least not while getting this much hang time. Alright, back to serious business. Got a basketball right here. It'll be object 1 on the second object. If object 2, myself, applies a force to object 1, then that same force will be applied according to Newton's third law by object 1 onto object 2. However, there's a big disparity in the mass. Object 1 is a very light mass object. Object 2, myself, is a larger mass object. So, I'm going to try to make myself about the same shape as this ball. See how that works for us. And I'm going to apply that force. You saw that force applied to the ball made it accelerate quite a bit. It really didn't accelerate me much at all. Newton's third law again, but this time we're going to use two similar mass objects. Joe and I have about the same mass, so Joe, get into a ball. I'll do the same. I'm going to face you this way so I don't throw you into something you can't see. Now I'm going to get into a ball behind Joe, and I'm going to apply a force to him. Notice that when I applied a force to Joe, it accelerated Joe away from me, but I got accelerated away from him as well, because the force applied to Joe ended up being the same force that was applied to me. Now you've seen Newton's third law in space. Now test it out on Earth. See you next time.
Okay, so Newton's third law of motion states, for every action there's an equal and opposite reaction. Notes for Newton's third law, action-reaction. Newton's first two laws of motion explain how the motion of a single object changes. Newton's third law describes something else that happens when one object exerts a force on another object. According to Newton's law of motion, forces always act in equal but opposite pairs. Action-reaction. The forces exerted by two objects on each other are often called action-reaction force pairs. Either force can be considered the action or reaction force. Action and reaction force pairs do not cancel each other out because they act on different objects. So action, reaction, they are forces that act in pairs. So the action here is air of the balloon is rushing down. So the reaction is the balloon is going up. Newton's third law of motion states, for every action there's an equal but opposite reaction. This means that when you push on a wall, the wall pushes back on you with a force equal in strength to the force you exerted.
Whether it's a lineman stuffing a running back or a safety colliding with a wide receiver, all NFL defenders have a single-minded goal: to stop the ball carrier. The object of making a tackle is you want to get the guy down and limit the amount of yards he's able to gain, especially after contact. When a tackle is performed correctly, it's not just a thing of defensive beauty, it's also an elegant depiction of Newton's third law of motion, sometimes called the action-reaction law.
Newton's third law says that each action or force has an equal and opposite reaction. So if I were to push against the body, that body is going to push back against me with an equal and opposite force.
An important part of Newton's third law is the concept of momentum, which in football is the mass of a player multiplied by his velocity, represented by the formula P equals mv. NFL players may not know the formula, but they're keenly aware of the role momentum plays in tackling. It's very important to have some speed and momentum as you're going in to make that tackle. The better you're able to use that to your advantage, the better you're able to make contact and get a guy down right away. In every collision on the football field, Newton's third law dictates that the total momentum between players must be the same before the collision as it is after the collision. This relationship is referred to as conservation of momentum.
The law of conservation momentum says that the P, the momentum before the collision, is equal to P, the momentum after the collision.
This law, represented by the formula P before equals P after, can be illustrated with a simple toy called a Newton's cradle.
In this case, we have displaced an initial sphere, and when we let it go, it has some momentum. It's mass times velocity. When it impacts the next sphere, that momentum is transferred through the middle three spheres and then passed on to the final sphere. And so because it has the same mass, it will move away with the same velocity that the first sphere impacted the middle three spheres.
The interaction of balls in a Newton's cradle can help illustrate what's known as an elastic collision, defined as one in which there is no loss of kinetic energy in the form of heat, sound waves, or deformation of the object. On the football field, collisions are typically inelastic collisions because kinetic energy is released mostly in the form of compression between the players' bodies and sound waves.
Inelastic collisions are the rule of the day. We see them all the time in football. That is, the energy of motion of two runners. After they collide, that energy is dissipated in deforming their bodies. That's like a spring. So some of your energy of motion went into that compression. You might have heard a loud snap from our pads. Some of the energy of our collision was transferred to the energy in the air that you hear.
While big hits look and sound spectacular, what's most important in tackling is stopping the ball carrier's forward progress. If your pads are underneath his and you're hitting on an upward slope, you direct the energy up and you take it back at the point of contact. Hopefully that's where the ball stops play in. Whether a tackle is successful or not, we can be certain that the same force is exerted on both players, and the total momentum before and after the collision is the same. For that, we have Newton's third law to thank.
Newton's third law of motion states, for every action there's an equal but opposite reaction. This means when you push on a wall, the wall pushes back on you with a force equal in strength to the force you exerted. Action-reaction. You constantly use action-reaction force pairs as you move about. When you jump, you push down on the ground. The ground then pushes up on you. It is this upward force that pushes you into the air. When rocket fuel is ignited, hot gas is produced. The gas molecules collide with the inside engine walls. The walls exert a force that pushes them out of the bottom of the engine. This downward push is the action force. The action force is the upward push on the rocket by the gas molecules. This is the thrust that propels the rocket upward.
Demonstration of Newton's third law of motion. According to Newton's third law of motion, to every action there is an equal and opposite reaction. Let us perform an activity to understand this law. Take a balloon and tie its mouth to a small piece of plastic tube with a narrow bore. Now inflate the balloon. Close the opening of the tube with your finger. Remove the finger and let the air escape. The balloon will move in a direction opposite to the direction in which the air escapes. Now fix the inflated balloon on the top of a toy car as shown here. Remove your finger to release air from the balloon. We observe that the car is moving in a direction opposite to the direction in which the air escapes. The car moves due to the reaction force exerted by the air on the balloon. This proves Newton's third law of motion. Click on the links provided for more illustrations of this law. Jet planes and rockets. In a jet plane or in a rocket, the products of combustion in the form of smoke are ejected outward with great speed. These gases under pressure apply a reaction force on the rocket and the jet plane in the opposite direction. This reaction force pushes the jet plane and rocket forward. Lawn sprinklers. In a lawn sprinkler, when water comes out of the curved nozzles, the sprinkler experiences a backward force and starts rotating, sprinkling water in all directions.
Question 1. Explain Newton's third law of motion. The third law says that forces always act in equal but opposite pairs. For every action, there's an equal and opposite reaction. If they're equal but opposite, why don't action-reaction pairs cancel? Action-reaction pairs don't cancel because they act on different objects, not on the same object. Equal and opposite forces acting on the same object would cancel. Today's activity are balloon races.
Today we're going to demonstrate Newton's third law of motion, which says every action has an equal and opposite reaction. It's the principle that sends rockets to the moon. If you want to try this at home, this is what you need. When I release my fingers, air pushes out of the balloon. That's our action. Our reaction is that the balloon moves with the same force in the opposite direction. If you want to learn more about Newton's third law of motion or ask me a question, check out scientistism.com.
So for the activity, we're going to calculate the speed of the balloon. To calculate the speed of the balloon, we have to divide distance divided by time. So the speed of the balloon can be calculated using the distance the balloon traveled and the time. Calculate the speed for each trial of the balloon rocket and then find the average speed of the 3 trials. So distance divided by time would be your average speed, distance divided by time, your average speed, distance divided by time to calculate your average speed. To get the average of all 3 trials, you're going to add those 3 trials together and divide by 3. Using arrows, show the direction of the action-reaction of your balloon. So the action is air is forced out of the balloon, and that air, that's the action, so the reaction would be the balloon moving to the left. Connection, let's think about this. Action-reaction pair in the previous slide is the action is the air going out of the balloon. The reaction is the balloon going forward. The balloon moves because of an unbalanced force. Unbalanced forces cause motion in objects. The force that moves the balloon comes from the air pushing on the balloon. For a STAAR test connection question, it says the picture shows an aerialist walking on a tightrope and holding a balancing bar. What's the action-reaction force pairs? So here the action is the aerialist pushing down on the rope, and the rope pushes up on the aerialist.